So once again, welcome students. Okay, good afternoon. And it's good to see that more of you have joined in today, right? As we wind down towards the end of your assignment 2. Okay, it's just a discussion. And yeah, we have a lot more students joining in. That's good to see. Right, so the ones who are already signed in, can you please maybe confirm if you are able to hear me loud and clear?
Yes, Sandeep.
Okay, that's good. All right. And if you are not able to, then maybe we are having some difficulties, could be the transmission and all that. Right. Okay, so we won't be delaying much. So let's get into it. So for those of you who are new, joining in today, so you should have viewed, or you would have viewed the videos I put out. That was for last week Wednesday as well as for Friday as well. So 2 videos which are available on YouTube, and that should have brought you up to par with today's discussion. Or just recapping, so are you able to see my screen as well?
Yes.
Okay, good. So that's the overview. Okay, we started with, and after that we listed down all the knowns. Okay, and then we started doing our calculation. The first one was the torque. Okay, that is the only load which is acting on the whole system, and then we determined the key length. Okay, which is part of the key analysis. Now, the next step is determining the hub. You could say the hub or the boss, or doing the analysis for that. Now, what we are trying to find from there is, okay, so I did a quick drawing for you guys. And let's see if I can pull this up for you. All right, okay, that's done in AutoCAD, right? So whatever you're able to see in green, that's the, what do you think that is? Looks like a, any ideas? Okay, feel free to unmute your mic and interrupt me, right? Okay. That is the shaft, okay, which has the, let me zoom in a little bit more, that is the, it has the keyhole in place, right? Okay, so what happens now is in that you'll have the key, okay, which comes and fit onto it. So as part of your key analysis, are you able to see this AutoCAD drawing?
Yes.
Okay, good, that's good. Right, so now you have the key. So pretty much I am guiding you towards your second part of your assignment, which is the drawing, okay? So, well, we all know what it would look like. So you'll have the shaft, and on top of that, you'll have the key. Now, how do you dimension the key? You know the width, you know the thickness, okay, which is given in the assignment brief. And what you had to do through your calculation was to determine the length of the key, okay? How long the key would be. And as you can see, half of the key is inside the shaft, half it is outside. Now, for the next bit of calculation, is that somebody's dog barking? I can hear. Anyways, so for the next bit of calculation, what you're trying to find is, is through the hub analysis, you want to know what is the hub dimensions, right? So I'll probably put up the hub for you, right? So there you go. Okay, now my question to you guys would be, see, there are 2 diameters to the hub. There's an internal diameter, there's an external diameter, right? Okay, now can you point out to me what would be the internal diameter of the hub be?
48 mm.
48 mm. Who was that?
Ibrahim.
Ibrahim. Okay, welcome. Ibrahim, you were the one who sent me the email, isn't it?
Yes, sir.
Yeah, so you managed to find the
Monday.
videos?
Yes, sir.
Great.
Thanks.
Okay. Right, so 48 mm. So the internal diameter of the hub is 48 mm, right? So your task is now to find what is the external diameter or the outside diameter of the hub. Okay, right. So going on to the hub analysis, we can say what we are trying to determine is the hub outside diameter, right? Determination, right? And then comes your calculation. Okay. Now my question again, the next one. This is really important. Look at this drawing. Okay, I have maybe I'll put the key and the, how about just the key? Okay, I'll include the shaft as well. Right. Okay, now I put it in different colors so that it is easier for you guys to visualize, right? So look at it and tell me, where do you think the hub will be at its weakest, right? So imagine now that you turn on the motor, electric motor, it starts to rotate. The shaft here, which is in green, starts to rotate, right? And where is it? Now the shaft starts to rotate. Okay, mounted on the shaft, you have the key, and they are rotating together because they are fixed to each other. And now the key is holding the hub or the boss in place. Okay, now that starts to rotate too. So where do you think, look at the drawing, okay, and try to speak in terms of stresses. So just concern yourself with the tensile stress, compressive stress, and shear stress. So where do you think the hub will be at its weakest point? Okay, at which point will it be weakest? Okay, just concern yourself with the diameter of it, right? Not the length, but the diameter of it. Look at the drawing and let me know very quickly. Okay, if you want, you could always refer to your notes. Okay, these PPT slides. So this is what you are able to see now. So we are trying to determine the outside diameter. So you can refer to these notes as well as to this drawing and just let me know where do you think it is the weakest. So
the part where the key will be inserted.
exactly. So where the part, which means, see, just minimize this. So as you can see, very good, Ibrahim. Right, so as you can see, the hub is uniform all around, uniform in thickness, I mean, right? The hub is uniform all around except the place where it is sitting on top of the key, right? So if you consider diameter all around, it is consistent except for the part where the key is. So just above the key, right, that is where the hub is most likely, if it is to fracture, I mean, if it is to fail, and so it is most likely to fail at that point, right? So what happens, there's a twisting action, in other words, torque. So once everything starts to rotate, so the hub, let's say the hub is weak at that particular point, so it will fail, and the failure will be as a result of tensile stress, right? So as you can see here, so evaluate using boss or hub fracture area above the key, right? So you will do the same thing once more. So in your calculation sheet, you could make a note, right, which says that it is assumed that the hub will fail at its thinnest section, which is directly above the key. Again, once again, you do not have to copy me on this. And there are some assumptions we are making. One of them is that we will assume that that the force acts at midpoint of the failing surface. What this means is, what the second sentence mean is, assume that the force acts at the midpoint. Midpoint means, here, if that diagram explains it more clearly, right? Okay. So midpoint would mean this, right? So halfway, just above the key, if you start moving upwards towards the end of, or towards the outside diameter of the hub, so midpoint, okay? So that is where the halfway mark. So let's see if I'm able to put a mark. So somewhere here, right? Halfway mark. So that is what you are saying is at the midpoint. So that's the midpoint, right? So that is where the failure will occur. Okay. Right. So that's what the second sentence means. The third assumption is that assume the radius at which the force acts. So the type of force here is tensile force, right? Okay. So what we need to do is, okay, this is a bit tricky, right? So what you need to do is, once again, going back to this diagram. Okay, what I'd like you to do is, are you able to, so from the midpoint, okay, from the midpoint, from the center of the shaft to the midpoint of this, right, wherever I made that mark. Okay, let's see. So that's RA, right? Please don't mind the silly writing, okay? That's RA, which is the assumed radius. So what I'd like you to tell me is how would you be able to calculate that radius? Okay, so start from the center and try to move all the way towards the midpoint. What all dimensions would you be adding? Okay, any suggestions? So what you are trying to find is RA, in other words, the assumed radius. Let's put that there.
So including the radius of the shaft, the height of the key, and
Okay, all right. So let's start with the radius of the shaft. Okay, and any one of you, if you're not clear as to what we are talking about, do let me know, right? So the first one you said was the radius of the shaft. Okay, so if you start with adding the radius of the shaft, it will take you from the midpoint to the circumference of the shaft. Okay, let's say. And what else will we add? That is, what else did you say? Plus
height of the key divided by 2, I think.
the height of the key divided by 2. Yes, it's very good. Why do you say divide by 2 then?
So because the radius of the shaft
Include.
is going up till the midpoint of the key,
Exactly.
which is inserted. Yes.
Yeah, exactly right. So what we'll say is now the half, it will be what? Half the key thickness, isn't it?
Height.
Yeah.
Yes.
Okay.
Yeah.
Thickness or height?
Thickness. Yes.
Right. Okay. So half the key thickness plus what else? This is the tricky part, right? Because we have no idea what is
The
the,
hub thickness.
yes, what is the diameter. So what is happening in this scenario? It says here, you'll have to guess this, okay? It says plus the half boss thickness above the key. Okay, so we will say half, let's just say half thickness above key, right? Okay, now this fellow here, I will probably highlight this in red. So, let's put this here. You will have to assume. So what you can do is, but now this is where your each individual assignment will be different, right? Because what we don't like to see is all of you using the same value. So you could use any value between 6 mm to, I'll just write to, not to confuse you, 6 mm to 9 mm, right? So here you could use any value. So the diameter of the shaft is 48. You'll find its radius included here. Add it to half the key thickness. You know the key thickness. Divide by 2, that becomes your second variable. That's the third one is half the hub thickness above key. That one you are free to choose any value between 6 to 9 mm. It could be 6, 6.5, 6.1, or 9 point, I mean 8.9 or 8 point whatever. Right, so any one value between 6 to 9 mm. Okay, I hope that is clear. So what you will have here at the end is, oops, R E. You'll have the assumed radius, okay, which is equal to okay. So once you find this out, so that's the first thing you do, right? Okay, let's look at our notes again. So you managed to do that. Okay. Right. So here, I just missed one part here. Okay, no problem. So what we will do is, let's see. So the force acting on the midpoint of the hub is given by the equation, right? Okay, now in terms of equations, so what do you know? Torque is equal to force times the distance, right? Okay, all right. So the only force, only load acting on the whole system, as I said in the beginning, is the torque. So torque is equal to force. Now, what kind of force will cause this hub to fail if it were to fail, right? So the force here will
Tensile
be
force.
tensile force, right? So Fe. So in other words, that's your equation. Control C. So I'm not able to. Okay, you know what? Tensile force is a pulling force from both sides, right? Okay. Compressive, you know, it's something pushing inwards, and shear is which we talked about during the key analysis. I'll just probably insert this here. Right, just put it in the center. Right, so torque is equal to what you will do is I'll make a note here that you guys need to find the tensile force, which is Fe. Okay, that's a task. So find the tensile force F. And yes, this is important. RA here will be the this will be RE. Okay, assumed radius. See, now you can see where the radius, assumed radius comes into play, right? So force, the force acting here at the midpoint will cause failure. So force will be equal to torque divided by RA, which is the assumed radius, okay? So now you find tensile force. Okay, what's after that? So okay, similar to the key analysis, this is what you guys will be doing. Right, so you will say that the tensile area which is likely to fail is given by, okay, when I say area, I mean this, right? Yeah, look at your diagram. The area is whatever is in given in red, okay? This part, red. So any assumptions, how would you find that area? Okay, that's basically, it's a rectangle, right? So area is equal to length multiplied by width for a rectangle. So in this case, the length would be what? Same as the
Key length.
key length, exactly, right? So that will be the length of the key multiplied by the this height here, the total height, okay? And we can write that height down as, so we could say it is, so the area of the height, the area of the hub above the key, in other words, which is area of the hub above the key, put them in brackets, is equal to the length of the key, okay, so multiplied by the height of the hub above key. Right, so area of the hub above the key, which another word means that whatever is in red, is equal to the length of the key multiplied by the height of the hub, which is above the key. So we could just give it a abbreviation, which is the something like height of the hub above the key, right? Mm, right, okay. Now that is known. So what did we say in the beginning as for the hub, the coupling? So this is made out of cast iron, right? So, right, this, which in other words, coupling, it includes the hub as well, right? So let's go back to here. So use the equation, which are the words at the material working limit, this which we have done, use equation. So stress is equal to the tensile force over the area, right? So what we're gonna do now is again use our stress equation. So this time, because it's a tensile force, so there will be tensile stress, okay, which will be acting on the hub height above the key. So the symbol for that is, see if I go to insert a symbol. Yeah. Okay, maybe I'll just write it down. Right, it'll be easier for you. So the tensile working stress of the hub is equal to, Right. So if you look at the tensile working stress, so given here, so the key was made out of steel. That's fine. The bolt is already predetermined. As for the coupling, coupling includes the flange. It includes the hub, right? So the tensile working stress given is 8 Newton per millimeter square. Okay. So you will input that here is equal to 8 Newton per millimeter square. Right. So now moving ahead. So what we're going to do now is, so the tensile working stress. Okay, I'm not able to find its symbol is equal to. So what did we say about the key analysis? Stress is equal to force over the area, right? In this case, the stress will be equal to, the tensile working stress will be equal to the tensile force, which you already determined here previously, Ft, right? Divided by the area, right? Which is, in other words, the area of the hub above the key. Okay, so the tensile working stress value, are you aware of that? Yes, you are. Okay, I just gave you, that's 8. The tensile force, are you aware of that? Yes, you are. Now the area of the hub above the key, the only variable left for you guys would be the height of the hub above the key, right? So when it says the area of the hub above the key, all you need to do is just input this equation here, the one above it, right? This one, it goes in here. So maybe I'll just highlight it so that you are aware. Oh, not the right color to use. So that. Right. So now the only thing left for you guys to do would be, so the only variable for you guys here would be the height of the hub above the key. Right. Okay, now I'll just give you a few minutes to just go over this. Okay. If you have any questions, feel free to ask. Okay. As for the hub or the Bose analysis, if you are not sure of any dimensions of any assumptions where I got that from, okay, do ask me. There are 23 of you. Okay, it's good to see a big number. So yes, any questions, feel free to ask. I'll give you a few minutes and then we'll try to continue. Okay, so I guess not. Right, so no questions from you guys. So we will continue and let's try to finish off with the last bit of thing left, which is the, so at the end, okay, I just missed something here. You'll have to let me know sorry about that. You're all here. So for some reason we all got cut off. Right. And so what you need to do is at the end, you need to let me know after finishing the hub analysis. Okay, so what happened was that meeting ended, so I had to restart another one. Okay, it's very frustrating at times, but we'll have to make do with whatever we got. Right, so we are done with the hub analysis. So at the end of that analysis, you should be able to determine what is the hub outside diameter, okay, which was the main idea from the hub analysis, right? Okay, and after that, following the hub analysis, we will move on to determine the what is the web thickness, right? Okay, as you can see here. So okay, if I open up my AutoCAD drawing, so that's the hub. Okay, I'll just try to hide everything and okay, that there is the web. Okay, right. So the web is that part of the whole flange which contains the holes for the bolts. Okay, so you have to determine how thick. Okay, so if I go to view and maybe orbit this. Okay, yes, so that is what you're after. How thick, through the calculations, you have to determine how thick the hub will be. Okay, what will be the thickness of the hub? So, okay, so when it comes to the Control C, so when it comes to the hub and flange analysis, so what you will do is just note this down. Next analysis is the flange. Okay, the flange analysis, what you're trying to determine is determining the flange thickness. Okay. Right, so I will try my best to end the things before 3 p.m., right? For the flange analysis. So what you're trying to do is, okay, so you're trying to determine what type of stresses will cause the flange to fail, okay, if it were to fail, okay, and what, through the analysis, you'll be able to determine the flange thickness. Okay, so the first thing is as for the flange, okay, looking at your notes, okay. In other words, the flange web means the same thing, okay. So shear of web from the boss, okay. So that is the web, okay. It will shear off from the boss or the hub, right? So for our notes, we can write down here that assume that shear force acts at the web and hub interface. Okay, when I say web and hub interface, it means whatever is here shown in red. Okay, that's the web and the hub interface, right? And is tangential, so the shear force acting is tangential to the hub. Okay. Right. So we know again from our equation that torque, T here means torque. So torque is equal to Control C. So torque is equal to the shear force, which is acting on the web, the shear force acting on the web, multiplied by the R. Okay. Okay. In other words, what will R be? Any suggestions? Or what do you think the R will be? The radius in this case. So look at your drawing. Okay, even this drawing would be able to help you out. Okay, so let's see the hub. Right, so what do you think the R would be? From the center of the shaft to where the interface, where the hub meets the web, what R should we take? Any one of you? Come on. It's a very easy one. Okay, so since nobody is making any suggestions, I will leave it to that, right? For you guys to determine what R should be. So just making a note here that you need to do calculations. Do calculations to determine the shear force acting at the web hub.
So will it be from the center to the top of the web?
Yes, once again, Ibrahim to the rescue for all of you guys. So yes, Ibrahim, what were you saying? It will be from the center of
From the center to the top of the web, the total
web.
length.
In other words, that is what? What dimension is that?
That's 48 mm plus the
Yeah. So that in fact, so yes, you are correct. So it is from the center of the shaft to where that meeting point is, right? For the hub and the web, right?
the web, yeah.
It is the outside, that is the radius of the hub itself, right?
Yes.
Okay. So good, you got that clarified. So this R here, I would just note down as the radius of the hub, right? Okay. So R hub. So all you need to do is find the force acting on the web. After that is, let's see, now, yes, again another tricky one. How would you be able to find this area in red? Okay, so the shear force is acting over a area, okay, which is causing, which would cause the failure of the web. So how would you be able to find that area, the shear area? Think. In the meantime, while you are thinking, I will add something to the calculation sheet, right? So the shear working stress acting on the web interface is, so stress is equal to, so so shear working stress is equal to divided by the shear area, which is, in other words, area of the web. So how would you find the area of, how would you find the shear area? Something of which you guys should be aware because you've done some things similar in high school, okay? Shear area, which is the area of the web. Cross-section area of the web, yes. Yeah, this part in red. How would you be able to determine that area? It's part of the circumference of the hub, right? But it has a thickness to it, right? So in other words, what is the web thickness? What is we are after? So how would you be able to find that out? There's 14 of you listening to me at the moment, so one of you should be able to pick that out. How would you be able to find it? How would you be able to calculate for that area in red, which you're able to see on the screen right now?
So using the web thickness and the diameter of the hub.
The web thickness and the diameter of the hub. Okay, so yes, the diameter of the hub and multiply by the web thickness. So in other words, what Ibrahim is saying very correctly is, if you open this thin strip of red, okay, which is enclosing the hub, okay, it turns out to be a rectangle, right? So in other words, that area, how do you calculate, is the circumference multiplied by the web thickness, okay? Right, so the shear area would be equal to, Ibrahim, what you do say, that it would be the thickness
The thickness of the web.
thickness of the web. That is what you're after, isn't it?
Yeah.
So I will say thickness of the web is the whole point of doing this flange analysis. Right, and multiply that by what? So the thickness part is fine here. How do you be able to find the circumference of this circle? Circumference will be equal to pi times what?
Pi times diameter. Yes.
Pi times diameter. In this case, diameter will be equal to pi. I'll just put this in brackets or parenthesis. Pi times diameter of the what? Diameter.
The hub.
Yes, diameter of hub. Okay, very good. Right, so again, I will make a note. I have given you all the details. So do calculations to determine the thickness of the web. Right. Okay. So that's it for today's class. Okay, right. So I hope the videos were being recorded. So this is session 3 for assignment 2, and later on I'll put this up on YouTube and give you the link on Moodle so that you're able to always go back and view the videos, right? Okay, so there will be a final session on Friday at 10 a.m. So we will finish off. I will try to finish off quickly. The last remaining thing is the bolt analysis. So here I will not be able, I will not, I mean, I will not be helping you with any of the analysis for the bolt, right? Okay, so in here, read through the notes. For the bolt analysis, what you need to determine is how many bolts would be used. Okay, either you can determine the bolt size or the bolt count. So in this exercise, the bolt size is specified to you. You have listed it down here in the beginning. Okay, all the parameters for the bolt. So what you can determine is the number of bolts. Okay, so either you are using 3 bolts or 4 bolts to hold this. So in my drawing, in my case, what I'm doing is I have 1, 2, 3, 4 bolt holes. So I'll be having my bolt count will be 4. So what I will need to determine is the size of each particular bolt. Right, okay. So, and for all the analysis, you would notice that it is the same, right? Same in the sense that you need to first find what type of force is acting. So for the bolt, number 1, determine what type of force will be acting on the bolt. Will it be shear force, tensile or compressive force? After that, determine what type of stress the bolt will be under, shear, tensile or compressive, and then find the number of bolts or the size of the bolt. Okay, it's very much simple. So determine the bolt PCD, pitch circle diameter. So pitch circle diameter means from the center of the shaft, if you draw a circle, it should be able to, the circumference of the circle should pass through the centers of the bolts. That's what PCD means, right? Okay, and the analysis is very simple. Torque is given here, use the torque, okay, to find the area of the bolt. Use the area of the bolt to find the number of bolts. Okay, simple. And once you have all the parameters, then you will be able to do this, what I have done, right? Determine or start doing your drawings, okay? Right. Any questions before I call it a day?
Sir, just a question.
Yeah, Ibrahim, go on.
So on part 2 of this assignment, so
Yeah.
exactly how many AutoCAD drawings should we deliver? Is it only the detailed drawing and assembly drawing?
Just do the assembly drawing here. What I have done is I have combined them all together, right? Are you able to see my screen, by the way?
Yes, sir.
Yes. Okay. So what I did was I do have the solution, so I was able to just sketch out. So you can probably draw it separately. You could draw the shaft separately, put dimension on it. You know the diameter of the shaft, right? As for the
Yes,
length
sir.
of the shaft, how long the shaft should be, nothing has been specified. So you could keep it as long as possible, right? Okay. Oh, it looks good on drawing. After that, draw out the harp. Okay. If you want, okay, normally this is what I do in drawings, right? I try to keep all my construction works in the drawing as well. Okay, so you could pretty much, and then put them all together, right? So what I've done here is I've used layers. Okay, so if you can always go and click on layers and turn a layer on and off, right? Okay. Does that answer your question, Ibrahim?
Thanks.
Right. Okay. So
Yes, sir.
yeah,
Thanks.
you could just put it separately and put dimensions on it. So the dimensions you put on your drawing should reflect the dimensions you have got in your calculations. Okay. So that will tell us that you have done everything correctly. Any other questions?
Okay, sir. No.
No.
That's
Okay.
also.
Right. So thank you all for joining me today. Right. And apologies for the cutoff in between. And the final session will be on Friday. So I hope to see all of you there. Right. Stay safe. Thank you.